Okay, so I've called this video the breakdown of lactate, and I'm already questioning whether that's the right name for it, to be honest. It's not so much about the breakdown of lactate, but about its formation. But in doing that, a number of things have to happen, and for some reason I decided to call it the breakdown of lactate. Anyway, I'm rambling. Let's get on. So, I'm going to give you an Emily analogy here. It's about something called a hydrogen carrier. So within the metabolic pathway of respiration, we use hydrogen carriers, and there are a fixed kind of number of hydrogen carriers, if you like. A little bit like when you go to the supermarket, there are a fixed number of shopping trolleys. So you pick up your shopping trolley, you do your shopping, and then at the end of your shopping, you put your shopping in the car and you put the shopping trolley back in the shopping trolley bay, and then someone else comes to take the shopping trolley. However, as represented by this little equation here, with shopping trolley plus shopping is reversible to an individual shopping trolley and individual shopping. If we were to imagine a situation where all of the shopping trolleys weren't returns, so if you take your shopping in your shopping trolley and instead of putting the shopping in the car and putting the shopping trolley back in the thing, actually you took the shopping trolley home and you never brought it back again, we would very rapidly run out of shopping trolleys and no more shopping could be done. Well, the same sort of basic principle can be said of hydrogen carriers. What they do is they pick up hydrogen ions and they carry them off to a different part of the respiration pathway, which we will learn in great detail later, but for now you don't need to know that. But what we need to be able to do is we need to sort of recycle them. So we need to take the hydrogens out of them and put them back into the world as empty hydrogen carriers or as little shopping trolleys. And that happens naturally in aerobic respiration because as you complete the pathway, the hydrogen carriers get emptied out and then they can return to pick up more hydrogen. But in anaerobic respiration, it wouldn't happen naturally. So we have to find a way of doing that. So what are these hydrogen carriers? Well, the hydrogen carriers in respiration are called NAD and FAD. NAD stands for nicotinamide adenine dinucleotide, and FAD stands for flavin adenine dinucleotide. Don't worry if those names don't stick for now. NAD and FAD are fine. Now, what you can see is that NAD will add a hydrogen, and so will become reduced to be NADH. Now, you will see this written lots of different ways. Sometimes it's written like this. Sometimes it's written like this. So becomes NADH2. Sometimes it's this is referred to as reduced NAD. Okay, to be honest, it really doesn't matter. There are any number of ways of doing it, but basically there just needs to be a means to show that it's picked up hydrogen, and the same with FAD. Okay, so this is what our hydrogen carriers are. Now, within the respiratory pathway, it's actually broken down into 4 sections. So we have glycolysis, which doesn't need oxygen. So that's the bit that can happen in both anaerobic and aerobic respiration. And then the link reaction, the Krebs cycle, and the electron transport chain. Now, what happens in these processes is in each of these stages, hydrogens are put into the hydrogen carriers. Okay, so we reduce a whole load of hydrogen carriers, and then they go off to the electron transport chain, where the hydrogens are taken out of them, and then the NADs can return to the top and keep on going. But if we were to stop here, then we don't have that recycling process. So the anaerobic pathway has to find a means to recycle and essentially empty these shopping trolleys. So if we have a little look at this, what is happening is glucose in glycolysis. So this is what this is. We are in glycolysis now. And what happens is glycolysis literally means splitting glucose. So glucose is split into 2 molecules called pyruvate. And in doing so, it fills up a couple of shopping trolleys, or it reduces some NADs. Now, what's quite clever at this point is that the pyruvate needs to then either go to form lactate in the means of animals, or it goes to form ethanol in plants. Okay, so if we look at animals and if we look at plants, what happens is the pyruvate will return and will become lactate. Okay, but in doing this, what it does is it actually oxidizes a reduced NAD. So what you can see is that by turning the pyruvate to lactate, we are emptying those shopping trolleys so that then the next glucose can be turned to pyruvate and can fill up the shopping trolleys. Likewise, in plants, as we go to form ethanol and CO2, exactly the same thing happens, and we empty a shopping trolley, or we oxidize an NAD, and that then allows this process to continue. If that didn't happen, then the process would be limited by the amount of NAD that was available, and that would make it potentially very short-lived.